Hello, my name is Mason Cipollini with my lab partners Colin and Leif. This is Lab 2 for OPTI 471B, where we will discuss the procedures and results from our experiments with Gaussian beam profiling and propagation.
The laser was first aligned parallel to the optical bench, following the procedure used in Lab 1. A pinhole placed on the optical rail was used to evaluate alignment at two positions along the rail. At the near position, the laser's XY translation was adjusted to pass the beam through the pinhole, and at the far position, tip and tilt were adjusted. This process was repeated until the beam passed through the pinhole at both positions, indicating proper alignment. The microscope was then aligned to the laser's optical axis. A fiducial was marked on the wall at the laser intersection point, and the microscope was placed on the optical rail. Using the projected internal crosshair and magnified laser beam, alignment was evaluated at two rail positions. Tip and tilt were adjusted to center the crosshair on the fiducial, and XY translation was used to center the beam on the crosshair. The microscope was considered aligned once both were centered at both positions. After alignment, the laser aperture was located using the microscope. The microscope was translated along the rail until the laser aperture was in focus, and the distance between the aperture and a fiducial on the microscope mount was recorded as 80 millimeters, or distance A. The microscope was then moved to a new position, and the knife edge was placed in front of it. The knife edge was brought into focus in the same manner, defining distance B. The separation between the laser aperture and knife edge was determined as E1, or 351.5 millimeters. A photodiode was then positioned behind the knife edge, and the beam was profiled by translating the knife edge across the beam with a micrometer while recording the incident power. Measurements were taken until the detector power plateaued. The knife edge was subsequently moved further along the rail, and its position was again determined using the microscope, yielding a second separation of E2, or 1064.3 millimeters from the laser aperture. The beam was profiled to this location using the same procedure.
From our procedure, we could take the data from each knife edge position and plot the curve. We can then derive the beam radii W1 and W2 from the difference of the normalized 16% and 84% intensities. These curves would also be plotted alongside their theoretical counterparts. As they display a very close fit, this means our experimental procedure is sound. From our experimental values and those found from the top three equations, we can use this quadratic equation and the quadratic formula to find our Rayleigh range. These equations can be used to find the beam distances Z1 and Z2, as well as the distance from the beam waist to the aperture. Because Z1 and Z2 are on the same side of the waist, the positive form of Z1 is used. Then, this equation is used to find the radius of the beam waist. These two equations are used to find the angular divergence of the beam and the radius at a certain distance. Finally, these equations are used to find the beam's radii of curvature. From these equations, we find a Rayleigh range of 641.6 millimeters, a Z1 of 420.9 millimeters, a Z2 of 1133.7 millimeters, a beam waist radius of 0.36 millimeters, a waist to aperture distance of negative 69.4 millimeters, an angular divergence of 0.56 milliradians, a beam radius at 10 meters of 5.61 millimeters. Finally, we receive the radii of curvature below for their listed distances.
In the second part of the lab, we characterize the beam propagation through a lens system. First, a lens is inserted some distance down the rail from the laser aperture. Then, with the laser off, the microscope is focused on the rear vertex of the lens and the position is recorded. Subtracting our position found for the laser aperture, the distance from the laser aperture to the lens is found and recorded at D equals 434 millimeters. Next, the lens is aligned with the optical axis of the system following the procedure from Lab 1. Turning the laser on, first the retroreflection from the flat surface is sent into the laser cavity by adjusting tip and tilt of the lens. Then, the reflection from the convex surface is similarly directed using X and Y translation. Example adjustments can be seen in the diagram. With the lens aligned, the microscope is placed back on the rail with a viewing screen to observe the image. It is then scanned across Z to find the position where the projected spot diameter is the smallest, corresponding to the beam waist. This works because the microscope is imaging a cross-section of the beam, and the beam waist is the narrowest part of the beam. With the beam waist recorded, the beam can be profiled using the same procedure as part 1, but this time the E1 position is in front of the beam waist, and E2 is behind the beam waist. At each position, a knife edge is inserted, and its position recorded using the microscope. We chose an E1 of 585 millimeters, which is 78 millimeters in front of the beam waist, and an E2 of 937 millimeters, 274 millimeters behind the beam waist. Then, the microscope is replaced with a photodiode, and the knife edge is scanned across the beam in the X direction using 20 to 50 micron increments. Shown in the second diagram is the setup of profiling the beam at E1. Finally, the beam diameter at each location is calculated as the difference in knife edge position at 84% and 16% normalized intensity.
From these procedures, we then fit the curve as we've done before, and we can see that it also provides a very neat fit with its theoretical counterpart, insinuating that our experiment is still sound. We use the same equations as our experiments without the lens. The only difference is that the Rayleigh range of Z1 equations will be calculated using their negative forms. This is because Z1 and Z2 are now on opposite sides of the beam waist. As such, we can find a Rayleigh range of 47.6 mm, a Z1 of negative 79.1 mm, a Z2 of 272.9 mm, a beam waist radius of 0.098 mm, a waist to aperture distance of 664.6 mm, an angular divergence of 118 milliradians, a beam radius at 10 meters of 20.6 millimeters, and the radii of curvature below. It should be noted that we also experimentally measured a beam waist distance of 663 millimeters.